Okay, in the follow-up video for Reddy's beam model, we continue the discussion. We mentioned that having a third order polynomial for displacement u will give us the correct form of the stress and strain, the correct being the compatibility of these quantities with the uh, boundary condition that we have on the top and bottom, assuming that there is no stress there. Okay, so let's continue with calculating the full strain to have them complete, basically following our kinetics map. Okay, so Eij is a matrix of 3 by 3. So the 1 A11 is the derivative of u with respect to x. So our u as mentioned here, so I have to differentiate this quantity with respect to x. So I rewrite it here. Basically, let's say I have u is z phi minus 4 gamma 3h square z cube. V is 0 and w is wx. So we have this. Now we come here and say derivative of this with respect to x is z d phi dx minus 4 gamma 3h to power 3 z cube. This turns out to, if I write gamma and I write these quantities for our reference here, gamma is phi, the rotation of the cross-sectional plane, plus the slope at a given x. So we come here, and if we rewrite it in terms of the y and w, actually I have to here say d gamma dx. I have to differentiate because the constant z is constant, and then we have this. So therefore we can say that we get z d phi dx minus 4 divided by 3h square z cube, and gamma is phi plus w. D gamma dx is d phi dx plus d2w dx square. And E12 is 0. E13 we already calculated. So I write it here again. Exz is equal to gamma, which is 5 plus dw dx 1 minus z over h over 2 square bracket. And this is symmetry. E22 is 0. E23 is 0. And then we have symmetry. So these are the, so just to make sure that this is clear, so this piece is E11 or EX. This is EXZ. And then we have symmetry with the condition that we have another 0 here. So diagonal only the first element we have. E12 is 0, E13, and then we have symmetry. So clearly we see that we get a non-zero shear strain, which we had non-zero shear strain in Timoshenko beam theory, but it was constant. As we see here, this shear strain or corresponding shear stress is not constant. It is a function of z. So it varies with respect to z. And that's exactly what we want. Not only varies, but it varies with a second order according to a second order polynomial, as we see here. And that is exactly what we want. So Reddy's model or beam theory, or sometimes referred to as third order shear distribution theory, because the third order comes from the initial assumption for the displacement. Now the corresponding stress gain, and the stress is according to this formula. And if you do that, then of course I will write it in terms of the more commonly used constant E modulus of elasticity and G shear modulus of elasticity, assuming again assuming that Poisson ratio is negligible. So here we say that this becomes E times EX, which is here. So basically this bracket comes here. 0. And this becomes 2G, 2, actually this should be divided by 2 here. And divide by 2 here. Okay. And therefore here I get G. Let me write it again. Phi plus dw dx for gamma 1 minus z over h over 2 square bracket. And E22 is 0 because remember that mu is 0 or considered to be negligible, and 0 and 0 and symmetry. So we get two stress component at the cross section of the beam, one normal to the cross section, which is E times this strain, and also the exz or sigma xz multiplied by g. So these are our only two stresses at the cross section. So as we know, if we integrate at the cross section, let's say here, if I have this cross section, and then I integrate sigma x and sigma xz across this cross section. So sigma x and sigma xz correspond to bending moment, and shear force. Okay. Uh, Now, if we look at here, the sigma x, I have to consider, sigma x has two terms. One first derivative, the second one has a second derivative here. So we have two types of moments here. One proportional to z to power 4 and z to power 2. So in other words, if I come here and say sigma x z dA, I will get one term proportional to z to power 2 because I have to multiply z to get the moment of the force times this z I get to power 2 and times this z I get to power 4 plus another integral over a proportional to power 2, sorry, power 4. So this will give us our traditional m. This will give us a kind of bi moment, they call it sometimes. We call it P. Similarly, for shear, so this is moment, and for shear is integral of sigma x z dA. No z because we are in just, this is the force, there is no moment here. And this gives me, if you come back here, you see that we have a z to power 2 term only, basically. And of course, a z to power 0 term here, which is phi. So again, we get two parts. One is the y plus, maybe I write this in complete form, maybe relatively, dA. This is our shear force, our traditional shear force, plus integral, this is again over a of z2 to y plus dw dx dA. Of course, we have some coefficient that I'm dropping them here just to, and this is, we call it Q. Not the first moment, but Q here is the shear or shear which is responsible for maybe warping or second order shear force that we have at the cross section. Okay, maybe here a sketch would be useful before we go further. That's a sketch that I tried to develop it using some AI sketching, and I try to bring it to the screen here. So what we are saying here that and this deform and deform should be exchanged here. So this not deform, the gray rectangle is the cross section, and the dashed line shows a sketch. This is not exact, this is just a sketch to show of the deformed cross section. So this is deformed, this is undeformed. And you see here that, any point that we have on the cross section has moved. It could be, kind of a warping here, as we have. Still, we are assuming these are u displacement in the x direction shown here as b1. And of course, here the b3 is upward, but we consider it downward. But that's not the point here. That is actually focus on this kind of deformation. So just I wanted to give you an idea about what we are talking about in third order shear theory, uh, uh, that a plane normally, originally a plane may become something like this, and or similar things out of the plane. You have variation on the top, on the bottom. Compare this to the initial Euler-Bernoulli, that this plane remains plane rigid and just rotates. But here we have made a lot of progress in terms of giving the beam more degrees of freedom to behave and to deform according to the applied load. Okay, so to have a complete set here, come here and define I2 as z squared dA, I4 as z to power 4 dA, because we get I4 as I mentioned, and I6 as z to power 6 dA. So basically the indexing of I similar, we are very familiar with this one in the strength of material, using Euler-Bernoulli, and this is the moment of inertia. Okay, and these are the higher, or if you can call it higher moment of inertia. Let's call this yeah, higher order and things. So if you go back here, based on my definition of m, um, for this, you get m, and these are subject to check and derivation approval. I'm giving you some ideas here that what you may get. And a simple, well, not simple, but a more proper displacement will give you these results for bending moment, shear, and so on. And P is EI4 d phi dx minus E or 3h square I6 d phi dx plus d2w or dx square. And V is G y plus dw dx, comma, times a cross section minus 4 h square I2, and q is g, comma, or phi dw dx I2 minus 4 h square I4, subject to full derivations. Okay, I may have missed a minus or some things, so please, if you are going to use this, please use it with caution. I'm not giving you the final formula, but one thing is that in this theory we have basically two unknowns. One is the w, the other one is if you go to gamma that we have here, for shear I need pi and w. So if I can calculate w and phi, the rotation of the cross section, and then the w, the deflection, then I need the governing equation for these two. And these are as follow. Or at least the relationship is as follow: d2 dx ei2 d phi dx minus, so this should be e c, we worked it out, I4 d phi dx plus d2 w dx square equal to minus q. This q is the load, and then you can solve. As you see here, the point that I want to draw your attention to it is that very minor change in displacement, but here a good change in displacement compared even to Timoshenko will give us a much more complicated uh, the, uh, differential equation to solve. Usually we have only this term, um, these two terms, or d to power d4 w dx4 for Euler-Bernoulli for w, and that's the only unknown that we have, deflection. But here we have the phi also. So please use the equations with caution after or subjected to full derivation. I'm not signing off for the exact form, but this is what we get. We get a very much more complicated equation, but not necessarily each term is meant to be given here in the exact form. But the main point is this addition here, and then the consequence correct form of strain, which is shown here, and the stress, which is shown here. This should give you enough background to discuss about this theory or other theories. Uh, as I mentioned, I have not done any numerical examples yet. I will do it in one separate video for all of them. But these are the main theories that you can consider for being in terms of their approximation or their assumptions. In the next video in this series, I will go through a formalism, shall we say, or a framework, which is not a theory, but that framework is interesting in the way that it tries and it does the job for creating a format, a framework for all of these theories. So we can make some assumption, the order in that theory, and that is CUF, CUF, Carrera Unified Formulation. And that is something that with some variation of a variable, let's say n, we can recover Euler-Bernoulli, we can recover Timoshenko, we can recover Reddy's, or even higher if we want. And that is, from that point of view, is interesting. So that is the subject for next video, or video 5. And after that, I will go through another approach that, here we have already considered displacement, and we work it out through strain and stress. This is very nice in terms of understanding of what is going on, but we have to make an assumption about the displacement and then live with the consequences, as you have seen in Euler, Bernoulli, Timoshenko, and here in third order theory. Sometimes these consequences are not according to what actually happens in the real world physics, but they are good in terms of simplified assumption and ease of solution uh, for the resulting equations. Um, as I mentioned, heavily we use the Euler-Bernoulli theory in engineering for that reason. But the other approach could be, this is a kind of bottom-up approach that we discussed so far. The other approach could be from energy point of view or variational principles point of view, using Lagrange method or equations. And basically we say that, okay, we don't want to make assumptions about displacement. We want the displacement be as a consequence of our energy distribution, the way that the beam will orient, adjust itself, and behave according to the strain energy, shall we say. And then whatever the resulting displacement is, let it be. So I don't make assumption and see what happens. I just, so that's it, kind of top-down approach. So that is the remaining discussions in this series. Okay, that's just to give you where we are going, where we are, and thank you for your attention. And hopefully, so far, these videos have been useful for interested people on this topic. Thank you.